Yeah, the third law states for every action there is an equal and opposite reaction. And those action-reaction pairs, we call it Newton's third law pairs. And they must be having these characteristics. Equal in magnitude, opposite direction, same kind. These are very important ones. And then after that you checklist the other ones too, which is acting at the same time, acting in the same line of action, and then must be acting on different objects, not on the same object. So if all of these are satisfied, then they are called the Newton's third law pairs. And Newton's third law simply stresses that no force comes into existence alone. They always come in pairs. And so we were actually like looking at gravitational force, right? The last thing we did? Yeah. Gravitational force is a force between any two masses. Between any two masses. We evaluated the force between Bryce and you, right? Yeah. Or you two? Okay. So you find the force between those two, and what was the answer? 3.09. 3.09 10 power minus 7 newtons is a pretty small force, so you just cannot feel it at all, because the grip with which they're sitting on the floor, on the chair, is much stronger. Not only that, they are being pulled from all the directions as well. They're being pulled by the table, they're being pulled by the desks and others sitting around. So you can't just look at only those two forces. Already they are small, and so they're not going to cause a big difference. Now, if you are considering the Earth and you, not to scale, if you're considering the Earth and you as the two objects, okay, let's find out yours. Yours is 100 kilograms, right? Mm-hmm. And the mass of the Earth is important. What's the mass of the Earth? It's 6 times 10 to the power of 24 kilograms. That's the mass of the Earth. Now you use the same formula to find out how much force is acting on him. What we normally call as weight. Weight is a gravitational force on him by Earth. And how do you find out? Using the same formula you done earlier. Gravitational force. The force is equal to G m1 m2 over d square, right? We did it. Now let's substitute everything. G is 6.67 10 power minus 11 times m1 is 100, m2 is a 6 10 power 24 over how far is he separated from the Earth? How far is he separated from the Earth? What did I say D was in the previous diagram? What did I say D was? Yeah. Between the centers. Didn't I measure the distance between their centers? Not from the edges? So basically D is the distance from your center to the center of Earth. It's not the physical distance of separation, right? And this distance from here to here is 4,000 miles. The distance between you and the center of the Earth is approximately 4,000 miles. It depends on where you are. Are you on the equator? Are you on the poles? So that changes a little bit. So it's 4,000 miles approximately, and of course we don't use miles. So changing miles to kilometers is 6,400 kilometers. Again, we don't use kilometers, we use meters. So changes to meters. And so you put 6.4 times 10 to the power of, not 3, but including the kilo, it is 6. Can you do this calculation quickly? Tell me the answer. Take your calculator out. What's the answer?
977.
977 newtons. That's a force between him and the Earth. In other words, the Earth is pulling him with 977 newtons. That is what we normally call as a weight. This is what we normally call as weight. So if someone asks you, what is your weight? You say 977 newtons. That's the exact answer. Because the question is weight, not mass. If somebody asks you, what is your mass? Then you say 100 kilograms. But what's your weight? Because weight is a gravitational force on him by the Earth. You've got to say this number as the proper answer scientifically. 977 newtons. Now, how do we normally find the weight of anybody? The weight of anything after you do the second law, you'll be more clear about it. Weight is mass times gravity. That's an easy way to find out the weight. Mass times gravity. So can you just do that now? Mass is 100 times 9.81. And the answer is 981 newtons. Now over here you saw 977 newtons. And here you're seeing 981 newtons. That's because many of these numbers are, so this is rounded. It's not exactly 6 times 10 power 24. This is a rounded number. That's a rounded number too. And I said that number can change depending on whether you are on the poles or the equator. The numbers are different. It's not always 4,000 miles. So you can see that they are there. So all you have to do is multiply your mass with 9.81. You get the weight. You get it? To find the weight, a gravitational force on an object, all you do is multiply by 9.8. You don't have to do it this way, but this is something that we will do in the next chapter. Okay? In the next chapter, we'll be talking about circular motion and gravitation. So we'll focus on this one more in the next chapter. Good. So what do you understand? So what is understood here is this is a gravitational force on him by the earth, and how much is he applying on the earth? Same force. So the gravitational force on earth by him is also same, 977 newtons. And that is Newton's third law pair. Find out if they are agreeing to all those conditions. Number one, are they equal? Are they opposites? Are they of the same type? Both are gravitational. And are they acting at the same time? Yep, they do come into existence at the same time. Same line of action. Same line of action. Same line of action. And what's the last one? Acting on? Is it acting on different objects? The force that is acting on him is acting on him. And the force that is acting here is acting on the earth. So they're different objects. So if all of these are satisfied, then you can consider them to be Newton's third law pairs. All right, so some of the examples of Newton's third law pairs, like importance of Newton's third law pairs, are this. How do you swim? What is the force that makes you swim forward? Say it again. Force of the water on you, but how did it apply a force on you? Because you applied a force on the water. So when you are actually like moving the water backward, you are applying a force on the water. Immediately Newton's third law pair comes up. The water is applying a force on you, and that's what takes you forward. So what is actually making you go forward is the water. The same way, a rocket that's taking off. What is exactly that forces a rocket to go up? Here.
It's applying force to the ground in the atmosphere initially in order to get lift.
It can even accelerate in space. It doesn't require an atmosphere. Atmosphere is in fact a botheration for the rockets because it offers a lot of resistance. So what exactly is pushing the rocket forward? Huh? Anyone? Think of what is the rocket doing?
Tilts. Firing.
Firing what?
Force on the earth.
No. Once it's off the earth, how can you apply a force still on the earth? I'm saying like it's in space and still it can like power itself. From where is that force coming? I mean, you've not thought about these earlier, but now think. This is the time to think. I'm prompting you with these questions, and now you say, all right. It is not the force applied on the earth and just like jumping up like as if you jump from the ground. No. What is exactly taking the rocket up is the gases, the burnt gases. What is the rocket doing? It is collecting some amount of gas, burning it, and it is ejecting the burnt gases downwards. In other words, the rocket is forcing the burnt gases downward. What is the burnt gases doing on the rocket then? Pushing it up. That's it. Newton's third law of air. So what is taking the rocket up are those burnt gases. Do you get it? The fuel is burnt and is ejected out. And the force that rocket applies on the fuel is the same as the fuel applying on the rocket. That's what powers the rocket up. So you can see in many cases, what about an helicopter? An helicopter is hovering right there. Now what are the forces? What is actually keeping it there? What is holding it against the weight? I told you, helicopter has weight, it should fall, but it's staying there. So there is something pushing the helicopter up. So what is the helicopter doing in order to get that? The propellers are made to spin in such a way that it collects air and pushes the air downward. And when the air is pushed downward, what is the air doing? It's pushing the propellers upward, holding the entire helicopter up. So air is not something that is negligible. That's why they call it air force. Yeah, air force. It applies a lot of force. Air can actually apply a lot of force. So what is holding the whole plane up in the air? We'll talk about it maybe next year. But what is the force that is holding the plane up there as it is flying? Is just the force difference between the top of the wing and the bottom of the wing, caused by air. Air applies some force from the top, but a greater force from the bottom because of the shape of those wings. So the wings are shaped in that manner. That is why it is shaped like that. The bottom is flat, but the top is curved. And that causes a pressure difference, and that causes a force difference. And the force that is applied from below is more than the force applied from the top, and that's what carries the tons of weight of this plane. Imagine how much force it is. So the plane is actually like held in the air as it is flying. That's why I said air force. Tremendous amount of force. Okay? So you can see Newton's third law coming in so many places. Let's say, for example, suppose you're standing on an absolutely frictionless surface. Absolutely frictionless surface. You're standing there. And then I'm asking you, can you move? Move from there, walk. You cannot walk. You just cannot move from there. But what's the best way to move?
Friction.
Huh?
Move the air.
Move the air? Yeah, you can move the air. You can try to swim. Seriously, because you can just push the air and the air will push back on you and you can start feeling the thrust. You can basically do that and you'll start sliding forward. Or, yeah. Throw things, yeah. Remove your jacket and mighty throw. So as soon as you throw the jacket, you are pushing the jacket with the force. The jacket will push you back and you start moving back. Or just blow air. Right? So if you're absolutely on a frictionless surface, even that will make you go backward. Because when you push the air out, the air will push you back. Now, coming to the kinds of forces. So you understand Newton's third law properly, the pairs. Okay. Now, what are the different kinds of forces, the different types of forces? The first one is gravitational force. You already know that part of it. It is a push, it's a pull. It's always attraction. It's a pull by one mass on the other mass. It's a gravitational force. And then you have electrical forces. Right? Forces. Electrical forces. Have you seen electrical forces? Yes, no? Electrical forces. Let me do this. Yeah, you can actually see the electrical force in action here. Yeah, watch this. Can you watch it? Yeah, watch this thing and see the electrical force. Look at that. That is an electrical force. All right? Or watch over here. electrical force.
Oh, that's a shoot.
Borrow the tissue. I have to use a tissue because there was a plug in here which is missing. I'm just creating a plug. All right, you watch that. Now here is the water bending. Now how is water bending like that? And if I use it double.
He's a water bender.
You see that? Okay, you got it. Now, why is water bending? Anyone? Why is water bending? Why did the water bend? Anyone with your chemistry knowledge? Huh? Polar, yes. Water molecules are polar, which means the centers of the positive charges in H2O and the centers of the negative charges are not overlapping like most of their atoms. They're separated, which means they're polarized. That's why you say water molecules are polar. So what happens is when you have an electrically charged object, when I go near water, because water molecules are actually having plus and minus separation, it gets attracted. You can see its attraction always, right? And even here, the same thing that happened. So electrical force, electrical. Similarly, magnetic or electromagnetic. All these are kinds of forces. Then you have nuclear force. Now, what is a nuclear force? Nuclear force is a force between nucleons. What's a nucleon? What's a nucleon? Everything inside a nucleus. Everything inside a nucleus. They're called nucleons. So the protons and neutrons inside are called nucleons. Okay? So the nucleons are the ones which are inside the nucleus. And so protons and neutrons, they attract each other. Protons attract protons. Neutrons attract neutrons. Protons attract neutrons. They're very strong forces. The strongest force is this. So this is the strongest. This is average. And this is the weakest. Gravitational force is the weakest of all forces. But gravitational force is longest range. Even though it's a weak force, it can act distances. You can see the sun and the earth are actually under gravitational attraction, even though the distance is enormous. It's the longest range force. This one is average range. And why I say average range, you saw it yourself. Only when I come a little close, it will really act. If I keep a charge over there and another charge over here, yes, there is an electrical force, but it is so negligible. But when you come close, it can be very strong. Yeah. The strongest force, but it is shortest range. So the protons and protons, protons and neutrons and neutrons and neutrons, these attract each other only when their nuclear distance is close. Like when the distance between them is like 10 to the power of negative 16, 17 and all that, only then it will really show the effect. Otherwise it won't. So if I have a proton here and a neutron here, it's not going to really cause any nuclear force. You can have other forces, but nuclear force, no, is the shortest range. So all these are called field forces. Field force. Why they call field forces? Because they act even at a distance. There is no need of a contact. They're all called field forces because there is no contact required. Is that clear? So no contact required, that's why they're called field forces. So you can see in all those cases, I didn't make a contact. I was just nearby. And that is a field force. And then the contact forces are different types. Contact forces. Yeah, the word contact forces, you touch something and that object applies force on you. So I push the table pushes me back. That's a contact force. So when the table is pushing you back, that's called a normal reaction. What is your action? Your action is you are approaching the table and touching the table, and the reaction from the table is pushing you back up. So this is contact force, normal reaction. The word normal implies perpendicular. In math, normal means perpendicular. So normal reaction means it's a perpendicular force from the surface on the object. So if I'm going to keep this meter stick pressed like that on the table, I'm pushing the table down, right? Where is the normal reaction? It is vertically up, not along this, not along this, not along the meter stick. It's vertically upward from the surface. So the normal reaction is supposed to be straight up. If I touch the board like this, where is the normal reaction? Straight out. It's straight. You get it? So normal reaction is a kind of force, mainly because of contact. Tension, T or Ft, those are called, that's a kind of force. Now what is tension? Tension is a force that is set up because of a stretching action. If there is a stretching action, then that causes tension. All right? So for example, this. I'm pulling this. Now I've stretched it. When I stretched it, there is a tension that is building up inside. And that is what makes it come back. See? The tension is something that is holding against you. You're trying to stretch it, it is trying to hold against it. That's called tension. So if you take a rope and pull the rope, there's a tension built up in the rope. And the tension is going to be the same everywhere in the rope. Everywhere in the rope, the tension is going to be the same. It's not going to be different. Near your hands and further away is going to be weaker. No, it's going to be a joint thing. Right? Suppose you join hands together and then one person actually is being pulled. Everyone is going to be affected equally. The force of tension that everyone is going to experience is going to be the same. So normally tension is something that comes in a cable, in a rope, in a chain, and anything like that. And then the other kinds of forces, friction. Frictional force. What is friction? Friction is a force that opposes motion. Friction is a force that opposes motion. Friction is a force that, you can write down. Friction is a force that opposes the motion. Now what really creates a friction is the atomic kind of bonding between two surfaces, like that. You know, you think that this surface is smooth, it is not really smooth. You think the table is smooth, it is not really smooth. Microscopically, zoom it up, and you'll see that there are lots of, ups and downs here, and there are a lot of ups and downs here. Zoom in further, you'll find strands of atoms kind of dangling from this, and strings of atoms from there. So like this, those atoms are kind of creating a web block. You understand? So when I keep this meter stick on the table, it's not sliding off because that little grip that's established, that is what prevents the object from sliding away. Now, if I try to slide by force, see what's happening. When I try to slide one object by force, you see what's happening here? I'm trying to stretch those atoms, and I'm trying to tear those atoms away. And what are those atoms trying to do is to prevent me from doing so, right? Because of the interatomic forces. And that force is friction. The friction that is kind of preventing you from sliding off. So if I'm trying to push the book and it's not sliding yet, that's because of the atomic forces. Get it? Now, let me ask you a question. If I'm walking this way, which way is friction on my feet? If I'm walking in that direction, watch carefully. If I'm walking in this direction, which way is friction on my feet? Which way? That way? No, okay. Now imagine I'm going to demonstrate this, and Thomas poured some oil or soap solution on the floor. I didn't realize it. I didn't realize he poured something here because I was trying to demonstrate my walking ability, and he poured something very slippery, and I'm trying to walk. What will happen? I'll slip. Why? Because what I'm trying to do on the floor is this. I'm gripping the floor, and I'm trying to move the floor back. I'm trying to slide like this. I'm trying to grip and slide the floor back. And since I cannot slide the floor back, the floor is offering, so I am pushing the floor back. What is the floor doing? Pushing you forward. And that's what helps you go forward. So what helps you walk is friction. If friction is not there, you cannot walk one step. If friction is not there, so friction is sometimes known as a necessary evil. It is necessary because otherwise it will be a headache. You cannot walk, you cannot drive it. So what is the driving force of your car? Now you know the answer. Friction, not the gas, not the steering wheel, not the wheels, not the engine. It is just the friction of contact between the tires and the road. That is what drives your car forward. Because what the car is trying to do is trying to spin the wheel this way by gripping it. And because the grip is pretty strong, the wheel is not able to spin and instead is pushing the whole car forward. So the force, so if you have a car and there is, if the car is trying to pull the road backward, there is a force of friction that is acting on your car tires, and that is what takes your car forward. If that is missing, and you'll see that in a couple of months, if that's missing, you are anticipating a certain amount of friction on the floor, and so as you spin the wheels will start spinning because you're not getting this, and so you lose traction. Yeah.
Why do you call it necessary?
It is necessary because without force, like see, I'm keeping the meter stick here. Will that meter stick stay there? No, it's going to slide off if friction is not there.
No, I was talking about the evil part.
Oh, the evil part. Can anyone elaborate on that? Evil part. Cross-country guys, can you speak up? Swimmers, can you speak up?
Oh. Is it because
Now you got the answer, right?
Is it because basically he tires us out traveling?
In other words, in fact, even the gas. Where are you spending most of your gas in the car? It is to fight air resistance. As you're driving, there is air resistance trying to act on your car like that. And you're fighting that air resistance all the time. If your car is moving, you're beginning to experience this air resistance. So you are fighting the air resistance all the time, and that is where you're spending all your gas. Otherwise, you just need a couple of drops of gas in order to reach Texas. Because you just barely start the car. Now the starting is done. It already acquired a speed of 60 miles per hour, and then finished. You can switch it off. And it'll keep going because there's nothing to fight against, right? So keep going. And when you reach Texas, stop. See how much gas can you save in that? Because once you got a certain speed, and if there's no friction, what is there to fight against? Nothing. So you keep going. Friction is evil in that manner. You can see, what about cross-country runners? Where are they actually? Aren't they applying the force on the ground to leap forward? Yes, but why are they not kind of increasing in velocity continuously? Because they reach a point where the maximum effort they're putting forward is being killed by the air resistance. So if you're going to run with like fluffy clothes and all that, you're going to suffer because you will suffer more air resistance. So that's why runners will prefer to have, not too many clothes on, like, skinnier. Also swimmers. If you have lots of hair and you try to swim, it will drag you a lot more. And so what you do is like you try to wear what is that? Swim cap. Because then it will be, Good fluid dynamics will be there, which means what? No, less air resistance. And if your body is more hairy, take it off, and that will actually help you. You know, your body is more slippery, so it actually will be better. If your body is full of air, then that is going to harm you because air resistance is going to be big. Just to say a little bit about the cars, if your car is dirty, you'll spend more gas. If your car is nicely polished and smooth on the outside, you spend less gas. Think of the difference. Yeah, because your body, the car will actually fight more air resistance if it has got stuff on the car. Okay, if there is dirt on the car, it's going to fight more air resistance. Get it? Okay, so friction is a force which is necessary at the same time as evil. We are trying our best to get rid of friction in many places, like wheels and axles. You put ball bearings, you put all those things, right? Bicycle, you know, bicycle racing. Look at this bicycle, like how skinny it is. Look at the seat, very narrow. You know why the seat is narrow? I always wondered that when I was young. Why is that seat so uncomfortable? I cannot sit comfortably. I want a nice cushioned seat. I don't like this narrow thing. I can't sit on it. The reason why it is narrow like that and not like comfortable seat is that when it's a comfortable seat, your legs will spread out like this. So you're riding the bicycle like this. And you see how much air resistance you're going to experience. Whereas when the seat is narrow, your legs are in. And so you're riding the bicycle like this, so you're kind of pointed like that. And so you fight less air resistance. Get it? So it's all aerodynamics there. And so also you wear this special kind of helmet, which is meant to give you more aerodynamics. And if you're skinny, good for you too. So multiple factors helps you to kind of get the speed. You want to come and sit? No? So like this, there are multiple kind of forces. We'll see all those forces as we go on. Is that clear? Questions? You'll have multiple forces, many more forces. But if you try to look at it in a different angle, I think you saw that in a video. If you try to look all these things in a different angle, that means microscopically, there is no such thing as contact forces. Contact, you cannot make a contact between two atoms. You can just get close. So technically, contact forces doesn't really exist. That's also a field force. Friction is a field force. Tension is also a field force because they're all between atoms. Normal reaction, it's a field force. It's not a contact. So contact does not exist in reality, but for all practical purposes, we consider that to be a contact. Because I initiated the contact, when I went so close, it is regarded as contact. So physically, like to your eyes, is that making a contact? Yes. But microscopically, it is not. Okay? So if you touch somebody, if you go touch a girl and say that, I didn't touch you, I just came close to you.
Yeah.
So that argument won't work. Okay. So even if someone stabbed somebody, it is not a contact. He went so close. He went so close that the force of interaction damaged the other part more than the knife. That's it. So, but those arguments won't work in courts. Best thing is, there are certain things which physically look like a contact, and that's what we regard as contact. Get it? Quiet. Field forces are distinctly these. Because even from a distance you can say, oh, there's no contact. To my eyes, I don't see a contact for sure. But for these, you will definitely be able to visualize a contact because to your eyes, you don't see anything different. All right. Now coming to the second law. See how much concept is there, even in the first and third laws. There's no number work, but there's concepts. Now coming to the second law. Let's go to the second law. And before we start the second law, we need to restate the first law again. What is the first law? In other words, good. All right. I think I gave you another kind of statement too. In the absence of external, did I give you that one? In the absence of external unbalanced forces, the object will stay in the same state of motion, correct? Which means it will be at rest or moving at a constant. All right. Now, second law is just the other way around. In the presence, you can write it down. In the presence of an external unbalanced force, in the presence of external unbalanced forces, in the presence of external unbalanced forces, in the presence of external unbalanced forces, what's supposed to happen to the object? Will it stay in the same state of motion? No. It will change the state of motion. And what do you mean by change the state of motion? If it's already at rest, it's supposed to be beginning to move. If it is already moving with a constant velocity, if it was already moving with a velocity, what will happen if unbalanced forces are coming in? It will accelerate, which means it cannot go with a constant velocity anymore. It will have changing velocities, increasing or decreasing. Both can take place, right? So Newton's second law simply states that in the presence of external unbalanced forces, that means, okay, Newton's first law states when the net force is zero, when the net force is zero, two things can happen. One is V is 0 or V is a constant. These are the consequences. You can write this down. First law, net force. This symbol is sigma. Sigma F means net of all the forces acting. If it is 0, then V is 0 or V is a constant. Second law is when net force is not 0. When the net force is not 0, then V will change. In other words, there will be an acceleration present. There will be an acceleration present. So object will accelerate. That is for sure. So if the net force is not 0, the object has to accelerate. And right now we are talking about linear motion. In the next chapter we'll go to circular motion. Then we'll look at it differently. But right now, linear motion. So when the net force is not 0, the object will accelerate. That is basically your second law statement. In the presence of net external forces, the object will accelerate. And write down further. The acceleration is directly proportional to the net force. The acceleration is directly proportional to the net force. So F net is proportional to the acceleration. The F net is going to be proportional to the acceleration. That means what? If you push with a larger force, it's going to have a larger acceleration. So you apply a smaller net force, you have a smaller acceleration. If you apply a larger force, you have a larger acceleration. Simple as that. But will every object accelerate the same way with that net force? No. What is the other factor involved? Inertia, which is mass. So F net is also proportional to the mass. It also depends on the mass. The heavier the mass, you need more force to accelerate it. Get it? Or combining these two together, F net is proportional to mass times acceleration. So what is the F net going to do? It is going to produce an acceleration, and depends of course on the mass. Depends on the mass. So if you are applying a force on a car whose mass is big, what is the car going to experience? A small acceleration. Now if you apply the same net force on a bicycle of small mass, you apply the same force, what you applied on a car, on a bicycle now. Much larger acceleration. So what do you know about mass and acceleration by themselves? They are inversely proportional. Mass and acceleration are inversely proportional. Bigger objects accelerate less, Smaller objects accelerate more. So at a stoplight, if there's a truck and if there's a car, and as soon as the lights turn green, the car will be sure to kind of take the lead. That's what we do, right? We just kind of stand next to a truck knowing very clearly that the truck is not going to accelerate too fast. And so you can always go in front of the truck after that. So, right? The mass of the truck is big, and therefore its acceleration is going to be slow. Mass of something smaller will accelerate more. All right? So do you get this point clear? Good. Now I'm going to change the proportionality to an equality. Changing the proportionality to an equality. F net is proportional to MA, and F net is equal to KMA. Now, changing proportional sign to equal sign will always be accompanied by this K, which is called the constant of proportionality. It's called the constant of proportionality. You must have done these things in math. The constant of proportionality, coming in and changing a proportionality into an equality. To give you an example, the length of one's pants is proportional to the person's height, correct? Is that statement perfectly okay? The length of the pants is equal to, is proportional to the height of the person. Is that a proper statement that you can say clearly and everyone agrees with it? But can I just say length of a pant is equal to the height? That is definitely wrong, mathematically wrong. When you're putting an equality sign, then you're going mathematical. So now it is mathematically wrong because the height of a person is something and the length of the pant is something. So definitely there must be a constant sitting here. Once you put that constant, then it becomes an equation. And what is probably that constant? You can actually find out yourself. What is the length of your pant?
32.
32 equal to K times what's your height? In inches. Because you're using inches both ways. Your height in inches. 5 feet is 60. Then, if you're 5,
70 inches.
huh?
70 inches.
70 inches. So what is K then? K will be 32 over 70, which is 0.46. So that's the K. Once you know the K is that much, you can find the length of the pant required for anybody. All you need is height. So let's find the length of a pant of a person. The constant of proportionality is 0.46. Now, who's the tallest here? Colin? Who's the tallest here? Colin, what's your height? In inches.
74 inches.
74. So times 74. What's your answer here? It should work out roughly right.
30.
34, is that your pant size?
That's right.
Sure.
Crazy.
So the constant of proportionality is something that fits in and changes a proportionality into an equality. Get this? Okay. Now, this is Newton's second law's equation, but K takes a value of 1 through the definition of the Newton. K takes a value of 1 through the definition of the Newton. So what is the definition of the Newton? We're going to define the Newton. Write down the definition. Write down the definition. Yeah.
What's the rest of the second law? Like,
Rest of the second law.
yeah, you said like in the presence of external imbalanced forces, you said
Good
like
point.
an object will accelerate. Is that it?
No. It's completely, it has to be completed. So did you leave some space? In the presence of external unbalanced forces, the body is supposed to accelerate, and the acceleration is proportional to the net force.
Is that it?
That's it. acceleration is directly proportional to the net force, and you can also add it is in the same direction as the net force. The acceleration will be in the same direction as the net force. So when the net force is not zero, when there are unbalanced forces acting on an object, the object will accelerate, and the acceleration is directly proportional to the unbalanced forces. And the acceleration will be in the same direction as the unbalanced forces. So if an object is acted on by a net force in that direction, it's going to accelerate the same way. Good. Write down the definition of the Newton. Write down here, definition. Some of these things are not mentioned in books, so there's some going through all of it, so you get it clear. What is the definition of the Newton? Write down the definition. A force is said to be 1 Newton. A force is said to be 1 Newton. A force is said to be 1 Newton when a mass of 1 kilogram acquires an acceleration. When a mass of 1 kilogram acquires an acceleration of 1 meter per second square. I repeat, a force is said to be 1 Newton when a mass of 1 kilogram acquires an acceleration of 1 meter per second square due to the application of the force. A force is said to be 1 Newton when a mass of 1 kilogram. A force is said to be 1 Newton when a mass of 1 kilogram acquires an acceleration of 1 meter per second square due to the application of the force. So if mass is 1, acceleration is 1, the force is defined as 1 Newton, what's K? If this is 1, 1, 1, what will be K then? That's why I said K takes a value 1 when you define the Newton as a unit of force. So once you have defined the Newton as the force, you don't have to put the K in anymore because you know K is 1. And your equation is simplified to F net is equal to ma. That is what is written normally as Newton's second law. Why the K is missing from this equation now is because we have defined the force as 1 Newton. So if forces are measured in newtons, then this equation is perfect. But if the forces are measured in other systems of units, such as dynes, dyne was a force of unit of force. Dyne was a unit of force earlier. We have never used it. People in the past have used it. Ask your grandparents, do you know what a dyne is? They'll say, yeah, it's a unit of force. What's a Newton? I don't know what it is. So now we are actually learning Newton as a unit. Dyne was a unit that was used when we had centimeters and foot. Not very sure of that, but different system of units. When they had different systems of units, not kilograms and 1 meter per second square and all that, no. So if the mass is measured in kilograms, if the acceleration is 1 meter per second square, then the force is 1 Newton. Finished. So from now on, you're going to use only this. We're not going to bring the K in because we are measuring forces in newtons. So that's pretty much the second law. And remember this, it looks very small, but how you apply this into problem solving and all that, we'll see. Let me know if you have questions as well as I go on. Now let's start working out some examples, and you'll see how Newton's laws are coming in to explain stuff. Suppose I take a rope. If I take a rope or a string and I put an object here, such as say 5 kilogram. So I'm suspending a 5 kilogram object on the string. let's discuss the forces acting on the 5 kilogram. On the 5 kilogram. See, that's very important. When you are actually discussing forces, you must know on what object are you talking about, because multiple forces are existing at the same place. But you need to know where or which one. Okay, so if I say on the 5 kilogram, don't think about anything else. Don't think about what the 5 kilogram object is applying on anything else. Think of what is experienced by the 5. So if I ask you, what are the forces acting on you right now? You only think of the forces acting on you, not by you. Right? There's a big difference. So right now, on the 5 kilogram, what are the forces? Yeah. Gravitational force. Do you know the numbers for it? How many newtons? By the way, remember I told you W is equal to mg. This is another form of F is equal to ma. You see it? So if I release an object of mass m, it's going to accelerate with this acceleration specifically because it's 9.81 meters per second square. So instead of writing ma, we are writing specifically mg for the weight. So if you want to find the weight of an object, just apply mg. If you know that you're doing it on the earth. Yeah. What is this?
49.5.
You can just say 49, let's say 9.8 is the thing, so 49 newtons. So 49 newtons is acting downward, that is gravity acting on it. And always these forces act at the center of gravity or wherever it is acting. So right now, this force is acting at the center. That's why my force diagram starts from the center. Can you see that? When you draw forces, make sure your point of origin of those forces are properly indicated. Yeah.
Is there tension in the rope?
Yeah, that's the next one. So this object is acted on by 49. Obviously, you see that this object is at rest, which means there must be at least another force, right? According to which law? First law. Remember, don't mix up those laws. There's one more force that is keeping this object at rest, and that is the tension. So what is the tension doing to this 5 kilogram object? It is pulling it. And I told you the tension is the same in the string everywhere, right? So is there a tension here?
Yes.
Is there a tension here? Which direction is the tension here? What is this tension doing to the ceiling? So you put the arrows accordingly. You put an arrow this way indicating that this tension is pulling this object upward, and you reverse the arrow there saying what is the tension doing to the ceiling, holding the ceiling down. Make sense? So the arrow marks on a tension depends on which object you're focusing on. If you're focusing on this object, the tension is upward. If you're focusing on the ceiling, then the tension is downward. So that's all the tension, that's all the tension. But we are only concerned about this tension, which is force acting on the 5 kilogram. What do you know about the tension here in this particular problem? Is it 49 or less than 49 or more than 49?
49.
Why 49? What made you conclude that it's 49? It's at rest. So according to which law? According to first law, if it is at rest, net force is supposed to be 0. And therefore, tension is 49 newtons. So we discovered that there is a tension in the string, and that is 49. Simple. Okay? Tension is 49 newtons. Now let's say this whole setup is inside an elevator. This whole setup is inside an elevator. You're suspending this block, and it is inside an elevator. And elevator is at rest. If elevator is at rest, what's the tension? 49 newtons. Now let's say this elevator is on its way down. It's going down at 2 meters per second. If the elevator is going down at 2 meters per second, tell me what is tension. If the elevator is going down at 2 meters per second, what is the expected tension here? Say that again.
49
Why did you conclude it's 49?
because still exerting the same force on the, or it's still exerting the same force on the 5 kilogram block, right?
Yeah, but what made you conclude that? That's my question. You're saying the same thing again. You said 49 and you're saying the same force. But what made you conclude it's the same force?
Nothing changed about it.
Can you be more precise? What you have to make a proper conclusion. Yeah, you made a conclusion that it's 49. This is right answer. But now tell me what made you conclude that it is 49? Very simple. Yes.
It's not moving relative to the tension.
No. Yes, Michael.
The object is still at rest.
No, it's moving at 2 meters. This block is moving at 2 meters per second.
How is it?
It's moving down at 2 meters per second. Yeah.
It's the same mass.
That doesn't make it different.
Has a constant velocity.
Has a constant velocity. Again, Newton's first law says what? If an object is at rest, the net force should be 0. If an object is moving at a constant velocity, the net force should be
0.
That's the conclusion. The first law coming in to help you here. So you see, when it is at rest, tension is 49. Why? The net force is 0. What if it's moving down at 2 meters per second? It should be net force 0 once again because it's going at a constant velocity. What if it's going up at 5 meters per second? What is tension? 49 again. It's 49. You can see that. It's moving at 5 meters per second means what? It's moving at a constant velocity, up or down. Constant velocity implies net force should be 0. And that means both of these should be equal to each other. And remember, this is not the pair of this. It is not. Because tension is a kind of force, gravitational force is a totally different kind of force. Okay, they are not equal. I mean, they're not Newton's third law pair. Now, what if it is accelerating upward at 2 meters per second square? Now, is it accelerating?
Yeah.
So, which means,
It's not a bad.
is the net force 0? No. Now you bring in which law? Second law, that the net force is supposed to be ma. So for this particular situation, T, you don't know. But then you have to look at it this way. Which way is it accelerating? So which one do you think logically is bigger, this or this? Why? Because the net force has to be in this direction if it has to accelerate in the same direction. Correct? The net force has to be in the upward direction because it is accelerating in that direction. So the net force is equal to the mass 5 kilograms times 2 because it is accelerating now, not 0. So the net force, how do you write the net force when this is the higher one and this is the lower one? Net force is T minus, isn't the net force T minus 49? T is upward, minus 49 backward, that's the net force, is equal to 10. So what is tension? 59. The tension should be 59 newtons if this is going to be moving in an elevator moving at 2 meters per second square. Now, let's say this. If it is moving down at 5 meters per second square, so what's the units? That's very important. If it is moving down at 5 meters per second square, now things are different. It's moving at 5 meters per second square downward. So which one do you think is bigger, tension or weight? Weight is bigger now. So the weight, 49, minus the tension upward is equal to ma, which is 5 times 5. So 49 minus 25 is equal to tension. So tension is how much? Tension will be much lower. 24 newtons only. And you see how we got this is by just using the second law straight away. Any questions on this? So you can see in an elevator, these are the situations.
Where does the other 5 come from besides the 5 kilograms?
5 is the mass, 5 is the acceleration.
Oh, the acceleration.
The acceleration is 5. And that's a mass 5. So you can see how the equation is set up. It's always good to do it this way. The bigger minus the smaller is equal to ma. Okay? It's better to do it that way. Don't use sign conventions and mess things up. Because sometimes the force could be in this direction. Alright? Awkward direction. So then you'll be wondering, like, will I consider this as positive or negative? Or, will I consider this as positive or negative? So confusions can come. The best way to get rid of confusion is bigger minus smaller equal to ma. Like, for example, you weigh 70 kilograms. Suppose you weigh 70 kilograms. One student is pulling you from behind at 500 newtons, and somebody else is pulling you from front at 700 newtons. Which way will you accelerate? Forward. What's the net force? 700 minus 500 is equal to 200, and that's equal to ma. His mass is 70. 200 is equal to 70a, and so you can find out the a. So with what acceleration is going to be moving? Is this clear? Let's come back to the elevator again. There's a weighing scale on the elevator, right there. That's a weighing scale on the elevator. And a person is standing there on the elevator, or on the weighing scale. And let's say the elevator is at rest. And if the person weighs 70 kilograms, 70 kilograms person. So what is 70? What is the weight of the person? Do it soon. Do it quickly. What's the weight of the person? Huh?
7.
Mass is 70 kilograms. What's the weight of the person? 686.
All right.
Now you know what to do, right? This is the mass of the person. That's the weight of the person. So the gravitational force that's acting on him is this. Now, is there any other force acting on him?
Floor pushing up.
Which one?
Floor pushing, or the weighing scale pushing
The scale pushing him up. The scale is pushing him up with a force which is a normal reaction. By the way, I ask you this question. What does a weighing scale measure? What does a weighing scale measure?
mass, weight,
Does it find your mass or weight?
mass.
I mean, let's say your weighing scale is calibrated in newtons. Will it measure your weight?
Yes.
Yes. So if I have a weighing scale, and I hold it in my hands, will it take your mass or take your weight? A weighing scale will not measure your weight. Totally wrong. A weighing scale will not measure your weight. Because if it was measuring your weight, you're holding the weighing scale and it should read it. What does a weighing scale read then?
The force that you
If I'm holding it like this, it will read 0. I'm using it though. I'm using a scale, but it's reading 0. Yeah.
The force of exerting on you.
The force that it exerts on you, that's it. It records only the force it exerts on you. And how does that force come into existence? Because you applied a force on the scale. Like if I hold the scale like this and push the scale down with my thumbs, will it read something? Because I'm pushing the scale down with my thumb, so the scale is applying a force back on my thumbs, and that is what is registered. So what does a scale weigh? You can write it down somewhere. It records a normal reaction only. A scale only reads your normal reaction. That is why when you hold it in your hands without pushing on the scale, it will read 0. Because you're not pushing it, so it's not pushing you back. Now when you stand on it, you're actually using your weight itself to push the scale. And that means that time, of course, the normal reaction is going to be equal to the weight. But if it is somewhere else, it's not going to read the same. So normal reaction is upward. So what do you know about the normal reaction in this scenario, like at rest? What is normal reaction? It's 686 newtons. The normal reaction, that is the force from the scale on you, is 686 newtons. Why? Because the net force of these two should be 0 at rest. Now you can answer all the others. Moving at 2 meters per second upward, what is normal reaction?
686.
686 newton, no difference. Downward, 2 meters per second, 686 newtons. Now, at 2 meters per second square upward. Now, if you are in the elevator and you're standing on the scale and the elevator is moving up at 2 meters per second square, which one should, there are two forces acting on you. One is 686, the other is normal force. But are you accelerating upward? Yes, you're accelerating because the elevator is going up with an acceleration, you're also accelerating with it. So since you're accelerating in the upward direction, which one is greater, this or this? The normal reaction is greater. So NR minus 686 is equal to MA 70A. Can you figure out 70 times what? 2. 70 times 2. Can you tell me what's the normal reaction? What's the normal reaction here?
540.
Oh no. 826 Newton. What does this mean? That means you feel heavier. When the elevator starts going up, you feel heavier. And when the elevator goes down, you feel lighter. Get it?